Alrighty, well, hello. Hi. I never know how to start talking in a stream, so I'm just going to start talking, and I figure that'll work fine. Hello, I hope you're having a lovely week. Um, I okay, so before start going through some chemistry stuff, I wanted to talk about perfectionism because there's an actually reason for this, and I'm going to take a moment and close the blinds on the window because that is really bright. Mildly better. There we go. All right. Let's try this again. So, I want to talk about perfectionism, and this came to mind because I had a conversation with one of the students that I tutor. Because this is happens quite a bit in tutoring students. And hello, Daph. Hello. Yes, you're here to be the star of the stream. Yes, of course. So yeah, lots of times in just like practicing chemistry, going through problems, writing out mechanisms and such. A lot of students, and this is absolutely inclusive of me as well, because I for sure suffer under the burden of perfectionism, and oh my god, that's adorable. All right, y'all just gotta take a minute because this is the best part of the stream right here. Hi. Yes, my cats are always going to dominate my attention, and I'm not sorry. Right. So, perfectionism. Yes. Hello, recovering perfectionist here. So one thing that I notice a lot in tutoring is that, like, when I ask the student, it's your turn. You go draw up on the board. You tell me what happens here. There's a lot of nervousness around just tossing an answer out. Good lord, you so yeah, there's a lot of hesitation to just like try stuff, and like I understand this on a visceral level, because you don't want to be wrong. You don't want to look like you don't know what you're doing in front of your teacher or tutor or whomever, and like even even if you are on your own, you don't want to think of yourself that way, because that can be just really discouraging in a perfectionist mindset. And so like I super understand this, and I think because of that, and because I've been that for so long, I recognize how much like that mentality can hinder like effective learning, and it can slow down the learning process. Like you very well may get there, to the same level of understanding and skill, but I swear, if you are a perfectionist and that is like keeping you from trying stuff unless you're sure it's right, you will not get there as fast. And for sure, definitely talking about practicing chemistry questions, because so much of this is not based on memorization. It's based on procedural knowledge, on understanding the approach to problems, and just like the um, having good understanding of the rules that dictate how these things go. Um, and so it is, and especially in a one-on-one setting, um, it's so much faster. It's so much easier if the student will just try things. Like, I don't care if they're wrong. And this is a talk that I had with my student, is like there is no consequence to having a wrong answer here, to guessing incorrectly, because like I certainly do not think any less of someone who attempts a question and doesn't get it right. But what that does for me as the tutor is it says, okay, so like here's a gap in the knowledge. Here's something that we need to focus on and try to shore up the understanding in this area. And so it's really helpful for both student and for teacher to just try the things. And so I told them the other day when we were going over this, give them a bit of a spiel on perfectionism, that like just try stuff. I don't care if it's right. It's all useful. Everything you write on that board is useful, because if it's right, that's great. We can move on. If it's not, that's awesome, because we can talk about this. Because if you understand why you are not why you're not correct, like that is how you most effectively learn to be correct next time. And so that in the context of practicing and just like it, certainly anything, not just chemistry by any stretch. Um, you ever get to the end of a sentence and you can't remember how it started? But anyways, yeah. So like it makes for more effective practice, to just try stuff. Try your first impulse. If that doesn't go anywhere, just go back a step. Try again. And we were going over some mechanisms of aldol reactions, where you will occasionally get to a step where it's like, okay, I could do this thing. Use this carbon anion as a nucleophile, or I could use that as a strong base, because like it is a strong base and a very good nucleophile at the same time, because those two things have a huge amount of overlap in their properties and behaviors. But one of these, like using this thing as a base to remove a proton, an acidic proton, it doesn't actually get you anywhere. You can do it, and I said, like, I promise you, this happens in the reaction flask all the time. But it doesn't get you anywhere, because as soon as you use this to deprotonate, either you've made just the same species, just swapping protons back and forth, or the how you use it as a nucleophile. You attack this carbonyl, and then it gets kicked out immediately, and you just go back a step and you try again. So it's good for students to recognize that, like, that's a possibility, and sometimes you need to just like take those reactions to their logical conclusion, and once you figure out, hey, this isn't actually moving anything forward, then you look for other stuff that you can do, because that generally, like, these questions are set up in an undergrad curriculum so that you can like there is a correct way to get through this, and you can find a reaction path that will just go forward and then won't go back. Yeah, so that's that's something I wanted to talk about in the context of practicing chemistry. Like just try stuff in on your own time or on this stream. Like we'll just like sometimes I'll get stumped with stuff and I'll just draw it out and just try things and you'll either get to a good and rational answer or you'll get to a point where you're kind of stuck. Um, and then you just have to go back and try again. And that's all just like part of the procedure to go through this. And then once you've done it, 10,000 times, then you can kind of recognize those superfluous steps and skip over them and get to the good stuff. Um, but yeah, so it's like just like trying stuff and being wrong. It's fine. There aren't any consequences. Um, and so this has been like a big thing for me in the last several years is like recognizing that perfectionism and how it is holding me back. And so in my studying and practicing chemistry, like I am I'm much quicker at it now that I don't obsess over every single little thing I try, although sometimes that is still a struggle, I promise. But like this applies to lots of different areas here, like in writing as well. Like I've been, spending a lot of the last year and a bit, couple years writing papers on my work, and a lot of it has been extremely slow. I'm a really, really slow writer, in large part because of this perfectionism. And so I obsess over constructing these sentences just right and like trying to get to, a final product all in one go. And that just, it doesn't work well. It makes me a really slow writer, and so this is something I've been trying to work on because my professor has tried to get this across to me. Is that like it's not hard to edit a bad draft and make it better and go over things again and think about it more and make it more correct. It's not that big a deal to do it. It's work for absolutely sure, but it can be done. It's just work. But it is impossible to edit a blank page, and so I've tried to really take that to heart, and I've gotten much faster at writing in the process of like the last two like really big publications that I did, the last one of which was published last month. I think actually to the day. Lovely. So yeah, I am getting better at this. I am a recovering perfectionist, and I think there's absolutely a place for perfectionism in like polishing final products and whatnot. But if that's the case, which I'm not making a strong assertion either way, if that's the case, the place for perfectionism is at the end of the process. The beginning of the process will go much better and much smoother if you just say some stuff. And so yeah, I've been working very hard on that, and a lot of times this this leads to a lot of the proverbial red ink on the drafts that I send to my professor, and there's lots of corrections, but that's fine because like doing the corrections and edits is a hell of a lot less work than trying to write a finished product from scratch. And there's weird things going on with the focus on my camera, and it's a little bit distracting to me, but don't mind me. It's fine. Yeah. So I've been trying very hard to get over myself and get out of my own way, as it were. And that's included things like doing this stream. I don't do really very much preparation for this stream. That might be kind of obvious. But that's okay because this stream is a thing that's happening and it's something I enjoy doing because I'm an enormous dork and I really like talking about this stuff. Um, and I feel strongly that knowledge should be free, and uh, removing barriers to knowledge and promoting scientific literacy is extremely beneficial to society and to individuals. Um, and it's just something I like to engage in because science outreach is something that's very important to me, very near and dear to my heart. It's actually on my sweater. This is the Let's Talk Science sweater that I was a coordinator for them for a number of years, doing events and talking to mostly like grade school kids, lots of high school kids, and some adults and families as well, just like talking about stuff. Anyways, I am that. That's a rabbit trail. I was talking about perfectionism in the stream. I don't do a lot of that, and like you may be able to tell by my hair. This is that was dumb. But yeah, so if I'm on here and I'm just rambling, this is just me trying to get over my perfectionism. So hey, good job, me. Yeah, and so like these questions, these problem sets, I'll sometimes look over them a little bit before I start doing them. But most of it is just me thinking and oh god, that's bright, answering stuff in real time and talking about it. Because I'm trying to actively go against this urge to basically script everything that I say. Yeah, and in that vein, also, I recognize that I am not going to know the answer to every question off the top of my head. I'm not going to know the answer to every question in chat off the top of my head. I'm going to get some of these questions wrong, and I'm pretty okay with that. It's all right. I've screwed up in quite easy questions in front of entire classes of students, and that's been okay. Because like I say, the stakes are not just low; they're subterranean. It's fine. It's okay to screw up here, as long as you recognize that. As long as you're willing to recognize that the mistakes that have been made and try to correct them. Like this is a much better pathway to being good at something than perfectionism, because that just doesn't really do it. Okay, so it's a really bright screen and it's distracting. Sorry, as is fruit flies, also very distracting. Okay. All right. I am going to yawn. Yes. Okay. All right. So I kind of don't think that this is going to be a particularly long stream, but that is okay. Oh, hello, person asking for a friend. Hello, how are you? All right. So, yeah, if you got any questions, I should actually probably talk for just a moment about what this stream is. Yeah, awesome. I'm glad you found me. So yeah, pretty much what this is I am a PhD student in chemistry. I'm a few months away from getting my PhD, so technically not a doctor yet, but Twitch didn't ask, so that's fine. So yeah, obviously my specialization is chemistry. If you got any questions of any kind or any topics that you would like me to cover, I'm more than happy to do that. Otherwise, I'm just going to go over some problem sets that I've got and just kind of explain kind of my thought process and how I think about the questions. Um, yeah, so what field am I looking at going into? I am hoping to get a position as an instructor. I'm not particularly interested in uh, in being like a professor, not a research professor, anyways. No real interest in running a research lab. I've known enough people who do that, and I'm good. The part that I really love is teaching, and it's something that I think I'm fairly good at, and so I would love to get just a purely teaching position. I'm working on an application package right now for a teaching stream professor at a university, so that's in progress. About a week and a half away from that deadline, but yeah, so that's kind of my interest. In terms of the chemistry that I do, primarily synthetic chemistry, and then I kind of specialize in electrochemistry and crystallography. And I dabble in lots of things because, like, kind of once you get into these sort of holistic research projects that you just everybody does in grad school, the lines between the different fields of chemistry get pretty blurry. So like I do main group chemistry. I've done some inorganic chemistry, a lot of organic synthesis, mostly very air and moisture sensitive kind of chemistry. But R&D of pharmaceutical medicine, that's incredible. I would love to hear more about that. Let me know like what's been your schooling, how long you've been doing it, because that's extremely neat. Like, are you on kind of the drug discovery kind of stuff, like doing any computational models? Um, yeah, I'm asking a ton of questions, and you're typing, which is kind of not fair. But yeah, I would love to hear all about it. All right. While you're typing, I'll start doing a couple of these questions so that I'm not just sitting putting pressure on you for carrying the stream. But yeah, we'll get to it a little bit. There we go. Okay, so this one is starting out on just identifying and naming functional groups. So I don't actually have a lot of theory to talk about here because naming functional groups is largely just memorization, and that's not something I can really tutor. I can just do it. So looking at pseudoephedrine, my pharmaceutical friend, tell me if I'm pronouncing anything wrong or butchering anything here. So, in terms of functional groups, a lot of times what we're looking for is pretty much just stuff that's not carbon and hydrogen, because carbon and hydrogen don't tend to really do a lot. So we look for heteroatoms, which is anything except carbon and hydrogen. So like nitrogens and oxygens. Sometimes it is hydrocarbons in just kind of special or unique formats, such as one of the functional groups here is this. It's an aromatic ring called. There's a few things that you can call this. This is an arene or an aryl group. You could also call this a phenyl group. This would be a phenyl substituent on the carbon chain there. Got to take a moment. Drug discovery is my focus to do this. Medical nursing and chemistry. Fantastic. Yeah. So what did you get degrees in nursing and or chemistry? And so in drug discovery, are we talking about like just ab initio, like like computational programs, like screening different ones. Yeah, or I guess that would be that's a whole last question there. So I'll leave you with that. Um, yeah. So yeah, an arrow ring over here is considered a functional group. And next we have just an OH group. And this is a hydroxyl group. The well, hydroxyl or just an alcohol. The I think the technically more correct term would be the hydroxyl group, because if you're making a systematic name for this compound, unless it is the primary functional group, which there's a whole ranking list from IUPAC, the International Union of Pure and Applied Chemistry, I think. They have a just a priority order for the functional groups, and so if the highest priority one is a hydroxyl group, then that compound would be considered an alcohol and would end in the suffix "ol." So yeah, that's an OH group, and then we've got over here. This is an amine. Yeah, and so that's all of the functional groups on that molecule. All right, durabolin, commonly abused anabolic steroid. Okay, that's a thing. All right, so on this one we've got another phenyl group, or aryl group, or arene, whatever you'd like to call it. We've also got this here. And so this combination is called an ester. And esters are defined as having a carbon-oxygen double bond and a carbon-oxygen single bond to the same carbon, and then there's R group here and R group here. And I should take a moment to define what an R group is. So an R group is just it's a variable, essentially. So an R group can be more or less anything. But the one stipulation being that the first part of the R group is going to be a carbon. So this one, so for an ester, well, I'm going to backtrack just a little, because there could be occasions where like this R could be an H. It could be rather a hydrogen, and this would still be an ester. However, this one cannot be an H, because if that was an H, if I keep saying H, if this was a hydrogen, then this would be a carboxylic acid, and would no longer be an ester. So this has to be some carbon group in order for this to be an ester. This one could be a proton, but hydrogen, but pretty unlikely, honestly. Can't actually think of any that would be that. But anyways, maybe I'll look for one later. But at any rate, this is what an ester is. So, so our group is it's a variable group starting with C. Usually. Alrighty. So, alright, my job is to discover how med can be used to treat many different things, i.e. Adderall is used for narcolepsy, ADHD, binge eating disorders. Okay, cool. Okay, so you start, like you're in the part of the process of like just seeing what these things do. Okay. So I wonder, like, um, uh, is this like actual testing of these pharmaceutical candidates, or is this like computational work that you do primarily? All right. So other functional groups that we've got on this molecule. So we got an alkene, just a carbon-carbon double bond. It's a little bit of a marginal case to call that a functional group, but I figure it qualifies, and I think under most definitions, at the very least, I don't think you'd be called wrong for saying that that's a functional group. So that I would consider an alkene a functional group. Okay, and this guy here, this carbon oxygen double bond, that is a ketone. There's a lot of functional groups that contain carbon oxygen double bonds. So these are things like, forgive my writing, it's doing this on a mouse is not my forte. Eventually, I want to get like a little like tablet or something that I can have this on and actually write somewhat legibly. But we are not there yet, so we're just going to go with it for now. So yeah, ketone. Yeah, computational mostly. Very cool. Yeah, I've been trying to work out my computational chops a bit. Particularly the paper that I published last month had a fairly substantial computational component to it, just because we had to look at a lot of different energies of different conformations of these sulfur diamides. And maybe I'm just going to shamelessly self-advertise for a moment and put the link to this to my paper in the chat, because I can, because it's my channel. I can do that. So yeah, there's a link directly to the article that we published. It's an open access article, and so it's really long and extremely boring, and I'm sorry for that, but kind of not sorry, because it is very good science. Just boring as hell. That's all. All right. Okay. So. Yeah, functional groups with carbon oxygen double bonds. So ketones have the form. Oops, not that. That one. Okay, so it's a carbon oxygen double bond, and the carbon of that carbonyl must have carbons on both sides of it. So in this case, we got a carbon over here, we got a carbon over here, and so this identifies it as a ketone. Things like aldehydes, by contrast, they have the carbonyl, the carbon oxygen double bond, and the carbon is attached to a carbon chain on one side, but on the other, this is it must have a hydrogen, and that would be that would make this an aldehyde instead of a ketone. We can also have things like carboxylic acids. which is just very similar to an ester. I mentioned it before, but instead of having a hydrocarbon group on the end of this, it's got a proton, and a reasonably acidic one. So, for example, if we had, if this R group, which I'm going to erase here, if this was just a methyl group, a one carbon chain, then this would be acetic acid, which is just your normal, typical, just vinegar. Yeah. Yeah. Oh yeah, I was also going to ask my pharmaceutical R&D friend here, like what level of education did you have to get into that, and how long you been doing the R&D job for? Terribly curious to know. All right, so moving on down the line, aspirin. So we've got a few things here. So aspirin, being the acetyl salicylic acid, has kind of three functional groups. I'm going to set off the color just a bit so it gets a little less confusing. So on this end we have got this is an ester, because it has precisely the same general form as, well, the other ester that we had. There's this R group here is a carbon on this end, and the carbon on the far side of the oxygen is the aryl group. Like I said, there's multiple things you can call this: aryl, arene, phenyl, whatever. I usually just call it aryl. None of them are wrong, but yeah. And so this last one here, this is a carboxylic acid, because it has that same hydrocarbon, carbon-oxygen double bond, carbon-oxygen single bond, and a hydrogen, which is the same as this journal form here. So aspirin is acetylsalicylic acid, which comes from doing some retrosynthesis arrows that is an ugly hexagon, but it will do. Okay, so it's got carboxylic acid on this end. So it starts out as this compound. So it starts with a hydroxyl group instead of that ester group. And this is, and this stuff here is just called salicylic acid, which you will see in a lot of skincare products, actually. I don't know why, so don't ask, but yeah, so this is, I'm going to write out the name of ASA, acetyl acid. So that's the full compound. There is acetyl salicylic acid, and its precursor is salicylic acid. Now, salicylic acid is commonly and originally found in willow bark, because for a very long time, like folk remedies would have, if you had a headache or some such, you would you just chew on some willow bark and you get a dose of salicylic acid, and this helps to relieve the pain. The issue with salicylic acid was that it's fairly rough on your GI tract. It'll give you a tummy ache, and so I can't remember the name of the chemist who did this, but this was a very intentional uh, 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 modification of salicylic acid because of the observed effects that things like phenol, phenol being doo, doo, phenol being just a phenyl ring with a hydroxyl group on it, which I can't seem to draw right, but that's just me. Let's try this again. Oh, that is not at all what a hydroxyl group looks like. There we go. Yeah, so this is phenol. It was used as an antiseptic for a very long time, but is you know, modestly hazardous. It causes a lot of irritation, especially of soft tissues. And so because of the similarities of that to salicylic acid, this chemist thought, well, if we basically cover up this hydroxyl group, perhaps we'll retain the good effects and make it easier on the stomach. And so he took it and put the acetyl group, just acetylated the hydroxyl group, and aspirin was born, and has remained in use for a very long time. So yeah, anywho. All right, we're going to duloxetine. So duloxetine. So again, we're looking for heteroatoms, which is anything but carbon and hydrogen. That's going to be the first indication that we have a functional group. So we got a few here. So we got that oxygen, we got this whole thing here. All right, we've actually got quite a lot there. So many that I am going to color code these because I'm very, very fancy. Okay, so let's start with the ring. Now this is a naphthyl ring. So if it's just one of these 6-membered rings, it is a phenyl ring. But if it is two 6-membered rings that are fused to each other, and of course aromatic, not saturated. So all of these carbons would be sp2, trigonal planar, what have you. So yeah, basically two fused benzene rings make a naphthalene ring, and so the when it's a substituent, you call it a naphthyl group. This is also still under the umbrella of an arene. So yeah, any of those would be correct as well. Flies. Okay, so this group here with this little oxygen, this is an ether. And the general form of an ether functional group is oxygen R. And that's it. That's the whole thing. It is just an oxygen that has two single bonds to carbons. So the most common one would be what have I done? Good Lord. It looks like chlorine. Anyways, try it again. Just put the H2 up there. Oxygen, and we're getting off. Yeah, so this is probably the most common ether at least that I deal with. It's just called diethyl ether because it has two ethyl groups, and this oxygen in the center is an ether. Just used as a non-protic solvent, so it doesn't have any acidic hydrogens to give away or mess with chemistry in the reaction vessel. Yeah, very low boiling solvent. Boiling point is something 30s or 40s, I think. Very low boiling point. Extremely high vapor pressure. So if you spill a little bit on the bench top, just wait a few seconds and it will be completely dry. Yeah, I don't have a lot else to say about ether. It's fine. It does the job. Okay. Moving on. We have once again an amine. This one is, of course, a secondary amine because it is connected to two carbons. We'll get more into that later. I think I saw in this problem set there's some more questions on primary, secondary, tertiary, so I will explain myself then and not before. Okay, so this group here, I'm mostly sure is called a thiophene. I'm gonna look that up in just a moment just to make sure I'm not talking out my ass. Thiophene. Yes. Oh, good. I am ever so smart. Look at me. So, it's a 5-membered ring. And it's an aromatic 5-membered ring with a sulfur in that ring. That's all I got to say about that. Okay. All right. So this one we've got. Oh yeah, fentanyl. How lovely. What a pleasant thing to end on. So, when I was taking organic chemistry, one of my professors, he's an interesting fella. But I took more chemistry from him than from anyone else, and I think that went well for me. He was a good teacher. The most memorable lecture from organic chemistry was at the very end of the semester. He called it his illicit drug lecture because we've been working a lot on synthesis and retrosynthesis and just planning these synthetic routes. And so he put up a molecule on the board, and so we kind of just work as a class and be like, okay, how do we make this? And so we start with this whole molecule and then break it at various points to just show a possible synthetic route to it. And then after we did that, then he would tell us what we had suggested making, and one of them was fentanyl, actually. Yeah, interesting fella. Very memorable lecture. Not sure if I'd give the same one, but... okay, so these aromatic rings, we've got arenes. Not going to talk about those again. Here we've got an amine. Not going to talk about that again either. However, here we have something else. This is another functional group with a carbon-oxygen double bond that I forgot to put up there. But that's okay, because we'll put it down here. This is called an amide. So the general form for an amide is there's carbon, oxygen double bond, and attached to the carbon of the carbonyl, there's an amine. Let's change that to just R2. In this case, both of these R's could be carbon or they could be hydrogen based. It's one of the forgiving R's. Perhaps I should think up a different way to specify that, but that's okay. Yeah, so the amide is a carbonyl attached to an amine. Oh, I gotta say about that. Okay. Alright, drawing constitutional isomers for C6H14. I think this will probably be the last thing I do for today, because I am an EP boy. And one thing I found, I obviously I've not been doing this terribly long, but one thing that caught me somewhat by surprise was that doing these streams and working through these problem sets and just like explaining my way through these things, it's a lot of work as it turns out. Much more so than it's like tutoring somebody one-on-one, where I'm having like a lot of back and forth, a lot of, okay, what do you think of this? Then the student is carrying quite a bit of the burden of conversation. But in this format, it's just me. I'm all that we've got so far, unless there's some lovely people in the chat, like my lovely research friend here. So yeah, I get kind of fried and brain dead pretty quick. So yeah, the length of all these streams is going to vary wildly, and it's completely dependent on how I'm feeling. But we'll do a little bit more, and then I'm going to call it a night. Okay, so drawing constitutional isomers. So we'll start with the easiest, most straightforward one, and then we will talk about it some more. So 1, 2, 3, 4, 5, 6. So this is one of the isomers for C6H14. It has 1, 2, 3, 4, 5, 6 carbons. And if you count up the hydrogens, there's H3, H2, 2, 2, 2, and 3. And unless I am very much betrayed by my arithmetic, that adds up to 14 hydrogens. I'm going to take those off because those will get annoying later. Yeah, so when I'm starting to look at a question like this, start by looking at the formula. So C6H14. What I'm looking for here is some indication of, like, are there any unsaturations? Are there any double bonds? Are there any rings? Because the presence of either of those would change the ratio of carbon to hydrogen. So, for example, so this just a straight chain of hydrocarbon has 14 hydrogens, because you've got these two on the end here. The two carbons on the end each have 3 hydrogens, because the carbon has to have 4 bonds in order to be neutral. It gets deeply unhappy if it has anything except 4 bonds around it. So in just a chain that nope, that was the end of that phrase. In a chain, you will have two. You must have the ends of the chain where you have methyl groups, CH3s instead of CH2s, in order to fill that 4 bonds to carbon rule. But if you take this and instead make a ring out of it, so you take the 2 ends of that carbon chain and bring them together into a ring. So we've still got 6 carbons here. I'm going to draw this out fully so we can see what's going on. Okay, so 6 carbons. Okay, I'm going to abbreviate H2. But now, in the case where we have a ring, now all of the carbons, all 6 of the carbons, have just exactly 2 hydrogens attached to them. Because those 2 on the end now have, like, each of these now has uh, a an extra carbon-carbon bond, and so each of them kind of, like, loses an H. That's not how you make a ring, but essentially, like, it has to have fewer hydrogens in a ring than you would have in just an open chain, and so that means that the formula for this, which is just a cyclohexane, would be C6H12. And so in a hydrocarbon, which is like in a molecule that's made up of just carbon and hydrogen, you can very easily tell from the formula what the degree of unsaturation is. And that's something we'll talk about a fair bit more whenever I get around to talking about spectroscopy, particularly NMR. So the degrees of unsaturation for C6H14 is 0. There's no unsaturations, no double bonds, no rings, no nothing. And so in a hydrocarbon, you can assess the degrees of unsaturation by doubling the number of carbons and seeing how that matches up. Because in for degrees of unsaturation equaling 0, like in the chain, the number of number of hydrogens equals 2 times number of carbons plus 2. So yeah, C6, 6 times 2 plus 2 is 14, and so that tells us the degree of unsaturation is 0. Whereas in the cyclohexane, it's C6H12, so it's the number of hydrogens is equal to twice the number of carbons. And so that tells us at a glance that there is 1 degree of unsaturation. And that degree of unsaturation is the formation of a ring. And then if you get, like if the number of hydrogens is double the number of carbons minus 2, then you'd have something like this. I should say you could have something like this, because there's all sorts of options of what it could be. Yeah, it could be. Oops, didn't mean to erase that. So it could be a carbon-carbon double bond. If there's things like oxygen in there and you calculate a degree of unsaturation of 1, probably a carbon-oxygen double bond. Things like that. So, just a few things to consider when you're starting to approach these. But right now I want to focus on there we go, working out the different constitutional isomers for this compound. So a constitutional isomer, it just means that a different molecule with the same formula. So it's like taking the molecule and just rearranging the bits so it has different connectivity, but keeping the exact same formula. And so one way to do this is if you so start with just the most basic one. So this is just a straight chain of 6 carbons, and then it's got the hydrogens. So if you start with that, and one way to generate a new isomer is to take this final carbon-carbon bond and move it over here. And so that would give us 1, 2, Because if we number these, like 1, 2, 3, 4, 5, and 6. Whoops. That's actually a better way to describe this. So, yeah, definitely could call this just like taking carbon number 6 and detaching it from carbon 5 and putting it on carbon 4. So this would be like 1, 2, 3, 4, 5, 6 now. So this spoiler alert, you can go ahead and like attach the hydrogens that I haven't drawn. Just make sure every carbon has 4 bonds to it, no more, no less. And you'll find that, like, obviously there's 6 carbons here, but you find that there are again 14 hydrogens. So this is different connectivity, because now we've got 1, 5, and 6 are all methyl groups, CH3, and carbon 4 is now a methine group. It's just a CH, and then connected to 3 other carbons. And this is it's got different connectivity than our first structure. So this is a new isomer, and so now we can keep going. If we take carbon 6 and now we move it, like detach it from carbon 4 and put it on carbon 3. So now we've got 1, 2, 3, 4, 5. So now we've got this. So 1, 2, 3, 4, 5, and 6. Okay, so this is another new isomer of it. Now, I wonder, do I have... No. I don't think I've got any tools to like take an image and flip it, but that's okay. We'll survive without it. Because I bring that up because if you now take carbon 6, detach it from carbon 3, and put it on carbon 2, you do not have a new isomer, because we have this. So I'm not going to number these, because this configuration where you got 1, 2, 3, 4 carbons in a chain, and then 2 methyl groups coming off of that 4th carbon, that is precisely the same situation as this isomer. So 1, 2, 3, 4 carbons in a chain, and then the last carbon is attached to 2 methyl groups. So that is not a unique isomer. So can't do that. Oh no, I have just... There we go. 5. Okay. So now the next thing that we can do. So actually need to erase that too, because this is not how we isomerize. Okay. So the next thing that we can do to generate a new isomer is we can take carbon 5 and we can move that. Hold on, something's weird. 4, 5, 6. Yeah. Don't know what I was smoking, but that's... No, it will be smoking though. It's Canada, it's legal. Get over it. Okay, so now that this is drawn correctly, so we can take carbon 5. Excuse me. Right. So we can't move carbon 6 anymore and generate a new isomer. So now we can start again at the end of the chain and move it to a different carbon. So take carbon 5, disconnect it from carbon 4, and move that onto carbon 3 as well. And then we get 2, 3, 6. Okay. So now we get this compound. 1, 2, 3, 4, 5, and 6. All right, so this is a unique and valid isomer because this has obviously the 6 carbons that we draw on, and now it still has 14 hydrogens. Carbon 3 has no hydrogens. It is only connected to 4 other carbons around it. But carbons 1, 4, 5, and 6 are all methyl groups. 3 hydrogens each makes 12. And carbon 2 has 2 hydrogens, which makes 14. And it has unique connectivity because this one has 3 methyl groups coming off of carbon 3, or you could say it has a 4 carbon chain where it has methyl groups 5 and 6 coming off of carbon number 3, which is actually how we would name it systematically, which is the subject of the next question that we'll probably get into next week. But I just want to finish this up. So, now, so this is 4. We have got 4 constitutional isomers. I'm so sorry. I will stop badly impersonating the venerated Count Von Count. So, now, what we can do here is we can keep moving carbon number 5. Because when I'm looking at this, I'm kind of thinking, okay, so this is a thing over here. We can't really do much more with this carbon because it's already attached to 4 different carbons. Like, we cannot move carbon 1 and attach it to carbon 3 because that would be 5 bonds to carbon, and that is a cardinal sin. Don't do it. So what I want to do here now is I'll keep taking carbon 5, or you can take 4 or 6. It doesn't matter in this case because they're all just methyl groups off of carbon 3. I'm going to move that over to carbon 2. And we'll draw it down this way. 1, 2, 3, 4, 5, 6. Okay. And so now we've got carbon 1, carbon 2, carbon 5, carbon 3, carbon 4, and carbon 6. Excuse me very much. So, this looks different from all of the others. It has, again, 4 methyl groups in 1, 4, 5, and 6. And then each of 2 and 3 is a methine, a CH group. So again, we have preserved the C6H14 formula. And we've introduced yet another unique connectivity. So yeah, that's kind of just it. You just shuffle the carbons around until you find something new. Like I do this a little bit on the systematic side, but you really don't have to. What you have to be careful of is, like, make sure that you draw everything in the same orientation every time, because you can trick yourself really easily by, like, drawing 2 of the same molecule in just different orientations, and so you don't notice that they're the same thing. It's terribly easy to do. So one thing that will for sure help is number your carbons. I tell my students this all of the time. Just do it. I guess if you're making any changes to the molecule, it's going to help you so much to just keep everything straight by numbering it and being consistent with that. All right. So I think that is going to about do it for me today. Because there we go. Yeah, because I'm sleepy. Because it's been a long day, and my brain's ready to do less thinky stuff. So I'm gonna go do that. I will leave you with a view of the magnificent Daphne um, grooming and ignoring you as she does me. So I hope you all have a lovely night. This is asking for a friend. Thank you very much for coming in and just having some chatting. I would love if you came back sometime and talk more because I am a huge nerd and I like talking about this stuff. But anyways, I hope you all have an amazing weekend. Goodbye. Bye.